Hello again. Here's another installment of the AI Anatomy series. I'm Dr. Coates. Our focus today is AI architecture or structure. As always, let's begin with the why. As a doctor, you've spent years learning human anatomy and physiology, and biochemistry, pathology, neurology, etc. You are an expert on humans. AI developers aim to mimic, then match, and finally exceed humans. Therefore, there are a multitude of parallels and analogies to draw between AI and human structure and function. Doctors are experts on human structure and function. It follows that doctors are incredibly well placed to understand AI. In this video, we focus on AI structure. I like to think about AI as a pyramidal iceberg. Let's imagine it's 2056 and you are living in Asimov's future. You have taken delivery of your first home assistant robot. When it arrives, and because you are a doctor, the first thing you want to do is pop the hood and take a look inside. You open its calvarium to inspect its positron brain. You find a glowing, ice-colored pyramid of tiny, blinking circuits. This pyramid has 5 layers. These are the task, application, foundation model, the computational layer, and the chip layer. Let's start with the top layer, the task layer. In the real world, we interact with task agents. We experience AI as seemingly autonomous software entities, working unsupervised, like a puppet without strings. We ascribe behaviors to the task agent. We even say, "The GPT told me," or "The GPT recommended." However, what we interact with, the task agent, is merely the final form of layers upon layers of human endeavor. It is the tip of the iceberg. It is incredibly important to be curious about the much bigger structure that lies deep to the surface. Another useful analogy arises from Punch and Judy shows. Young and old alike delight in the puppetry. Toddlers are awestruck, and perhaps a little afraid of these seemingly autonomous puppets. School-age children are developing a theory of mind and have some idea that these puppets are a meta-representation. Adults fully understand that the puppet has hidden strings. We also understand that the better the puppeteer, the less obvious the strings. Similarly, with AI, the more autonomous the task agent appears, the more we are impressed. But, as Galileo might say, and yet it moves. AI puppets have strings, and we must defy conventional wisdom that bids us to pretend otherwise. One of my key goals is to enable doctors to see and examine these strings, so we can better jerk them. Returning to our layers, let's consider the task agent and its behavior. When a task agent presents behavior, for example, making a diagnosis given 5 discrete symptoms, this behavior is generative. Something new has been generated. Therefore, it makes sense that the underlying applications are loosely termed Gen AI. Deep to the task layer is the application layer. The application layer is where we find the Gen AI apps. We may be aware of different Gen AI applications from different companies or brands. In the noughties, we laughed about having a smartphone app for everything. Increasingly, there's an AI app for everything. For example, we all know about ChatGPT from OpenAI. Google's Brain and DeepMind developers teamed up, or twinned up, to give us Gemini. Meta have given us Llama and Meta AI. Stable Diffusion have given us Stability AI, a leading text-to-video app. Deep to the application layer lies the foundation model. For example, the class of GPTs. There's ChatGPT and Jobs GPT. There's Cody GPT and Accountant GPT. We remember that a GPT is a generative pre-trained transformer. A GPT is one of a family of LLMs, which are neural networks trained on large language datasets. A developer can curate the training data to ensure that the emerging app is expert at a particular task. However, the underlying foundational model for each of these apps is a GPT. You will be interested to learn that a neural net can be exposed to both words and images. Image-based foundational models include generative adversarial networks, or GANs. GANs are trained on image recognition. As they become more sophisticated, they can then work backwards to generate images from text. In summary, GPTs and GANs are foundational models underlying many of the Gen AI apps you will come across. Here, it is important to consider the training journey of an AI. Doctors should intuitively understand LLMs. Our pre-training is heavily supervised. We have years of examinations which fine-tune our knowledge and practice. After many years, we get to work unsupervised. Some of us even make new discoveries in our field of knowledge. As I like to say, doctors really are the OG LLMs. Like doctors, AI have to be pre-trained. Training is intense, expensive, and prolonged. Humans take decisions on which inputs are used, and which are omitted, and what weights are given to various features. AI are trained on the work of experts, like you. They mimic, match, then exceed doctors in practice. Therefore, the foundation model layer is clearly a product of human endeavor. An artistic radiologist could probably redraw sequence 5, image 6 of the last CT they reviewed. However, when an AI does the same, it is met with wonderment. This tendency is a feature of AI hype, which is a topic for another video. Foundation models run billions of computations, often in parallel threads. To make these computations, that is, to compute, you need complex circuitry or hardware. This brings us to the computational layer. This is the fourth layer. Let's return to our humanoid home bot. You've now managed to miniaturize yourself and entered its brain in a tiny spaceship. We will call our tiny spaceship the HMS Machine Learner. Mostly because Rocket Mac Rocket Face is already taken. As you fly around the humanoid's brain, you can see the nerves lighting up to transmit information, like a functional MRI. Your machine has advanced instruments that detect and record these signals. For example, you recently journeyed to the motor cortex. Your machine learned that when the humanoid was walking, a very specific pattern of nerves fired in sequence. You label this the walking algorithm. One day, the humanoid brain fails and is taken for repair. The technician finds you and your algorithmic space machine within the humanoid brain. They are able to transplant you into a new humanoid. Once there, you use the algorithms you've learned to drive the new humanoid and thus complete your studies. This analogy illustrates the algorithmic basis for the AI computational layer. It's not just software, like the Office packages we interact with on our desktops. It's software that captures lessons learnt. It is a step-by-step problem-solving procedure. It is an algorithm. However, the more complex the behaviors required, the more storage and processing capacity required, and the more computing power needed. Computational power is what is colloquially termed compute. Once you get past the cringe, it is important to be familiar with various metrics for compute. You will hear about flops, tops, and petaflops. The ops suffixes refer to operations per second. Clock speed is described in gigahertz and captures how hard the chip can be ran, given energy requirements. There are many other metrics. Importantly, compute is dependent on both hardware and software elements. So when we talk about compute, we are talking about both the computational layer and the chip layer. Which brings us neatly to the chip layer. This is the bedrock of all AI computation. It is also the hardware layer. Chips are essentially incredibly tiny transistor circuits in formation. They are the central nervous system of an AI. Like the human brain, which is organized into cortices, transistor circuits in chips are organized into cores for specialized tasks. Tasks fall into two broad groupings: memory tasks and processing tasks. These cores are further connected to each other in horizontal and vertical arrays. Wired circuits exist on the nanometer scale, which makes them smaller than a human nerve. The more circuits you have, the more calculations or operations you can do in parallel, or switch between tasks more rapidly. Like the brain, this complex environment has to be regulated to ensure optimal operating temperature and energy levels. Chips have also become more specialized over time. Big data requires more computational power, leading to the migration away from central processing units, CPUs, to graphics processing units, GPUs. Neural networks run more efficiently on specialized integrated circuits, or ASICs. This has led Google to develop TPUs, or tensor processing units, specifically for training AI. FGPAs are field programmable gate arrays, which have cost and energy efficiencies over GPUs. With this overview of the 5 layers of AI, what actions can we take to deepen our understanding? Think about an AI you have used recently. Your hospital may have introduced a dictation software, Copilot, pathology, or radiology AI. Take 5 minutes to think about what's under the surface. You could search online and ask basic questions for each of the 5 layers. For example, what is the Heidi AI Foundation model? Thank you, and please share this video with one other medic to help us prepare our community for the changes to come.